Hello everyone. How's everyone there? Hope you're doing as good as I am. And today I'd like to do a little bit of recapping. I want to cover the main points that I covered first with the black hole and then with the point. I think a little summary, a little synthesis is quite handy at this point. Would let you, you know, keep the main points that I was trying to make. Um, so here are the main points, just in bullet format. Okay. And what are we talking about? We're saying that, the black hole, regarding the black hole, what we have is a black hole. Um, they've never decided whether it's an object or a concept. Okay, that's the first problem we have. They have two definitions, essentially, or two notions running around in the literature and also in the popularization magazines. Black hole mass is a serious problem because it's a circular argument. Um, and I'll go over that in a second here in a little more detail. Um, the third one is that gravity in general relativity, it invokes Newtonian force. You can't do without Newtonian force in general relativity gravity. And then the black hole is also, by the way, that applies to black holes, okay? And then the black hole is a little surrealistic when they put this 2D black hole. They show you the hole from a frontal view, and they are supposed to superimpose that thing on in a 3D volume or a 4D volume, the 3D fishnet, if you can picture that in any way. And then that also takes us to the problem where, you wonder what the black hole is into, because if you're looking at the black hole face on, head on, the question is, what is that hole into? It looks like it's into space, and they have this thing going into Never Never Land. So that's a problem. What is it into? And then we also have the issue of, they have these black holes colliding. The collision creates transverse waves, which they pick up here on Earth. They get Nobel Prizes for these kinds of things. And it turns out that transverse waves can only propagate through solids, through rigid material. They can't propagate through liquids or gases. And so what they've done is they had to convert the space or space-time or both. They had to convert it into a solid. And that's that's already quite difficult to believe. You wonder how the poor astronauts don't scratch their elbows when they're out there against this rigid space. And so, yeah, transverse waves can only propagate through solids, and that's a problem. The other problem is that the waves are surface phenomena, and you don't find them inside the ocean. What we find inside in the body of the ocean, those are called currents, underwater currents. And so, transverse waves, you can't talk about transverse waves inside the ocean. And that's a big problem. It's a conceptual problem. It's mixing, again, what we find on the surface, which you could say is a 2D scenario, and they're applying it to the 3D volume and saying, oh, well, we're sending transverse waves through the ocean, the cosmic ocean. That's a serious problem. That's a conceptual problem, by the way. Okay, okay, so let's go here with the first one. I'm just going to go through these relatively quickly. Okay, here's the first issue. The first issue is that they what they do is they have this duality. Mathematical physics is plagued with dualities, and it's that they confuse the ball, the 3D ball, with the 2D hole. In other words, when you look at the hole there, the one on the right, lower right, you're looking at it head on. And the question is, what's on this side of the hole? See, they're treating the hole in that case, in that scenario, in that vision. They're treating it as if you're looking at the surface of space-time, as if you're God and you're on the outside of space-time, and you're looking at it head on. And the other one, the ball, it's a standalone 3D object. And so the question is, which one is the black hole, the official black hole? And you can see some testimonies there. The first one in each case for the ball and for the region are very official. The first one up there says black holes are a great amount of matter packed into a small area. A star 10 times more massive than the sun squeezed into a sphere approximately the diameter of New York City. That one comes from NASA. Then the other one, the black hole as a region, the first one, black hole is not a tangible object but a region in space. That comes from the Max Planck Institute. So these are official statements. And you can see that we have this duality. We have the duality between the ball and the hole. And they use both of these. And you have to be careful not to be confused by them first. And second, you know, there you have a little material to throw at a mathematical physicist if you ever get a chance to confront one. Say, look, you know, is your black hole a ball or is it a hole? And then the hole is 2D, the ball is 3D. You know, can you make sense of this? You know, and if he doesn't understand, just bring Bugs Bunny there. He can show him the difference between his hole and the ball he holds in his hand. Okay, so just be aware that this is a serious problem because people don't realize what's happening here. What's happening here, they take this star, this enormous star, supposedly, they shrink it, shrink it, shrink it, and some people go all the way. In fact, that's what the math tells you, that you should go all the way and end up with a singularity surrounded by this spherical event horizon. That's one scenario. The other scenario is that, well, it shrinks, but it leaves something in the end. That's a very compressed, very compact ball. You know, you go into this neutron star phase, and then it continues shrinking until it turns into a black hole with a lot more mass, okay? Because the original star had a lot more mass. And so you have these two versions. You should be able to distinguish between them. You know, you can't have both, you know, your cake and eat it too, okay? Okay, what's the second problem? The second problem is that we have mass. And here I've got a little circular diagram for this. Black hole is supposedly made out of mass. It has other features too. You know, some black holes have other features, but all of them have mass. So if you ask a mathematician, what is a black hole made out of? He should be able to tell you, look, it's made out of mass. Straightforward, because that's all a black hole has, for sure. And the problem is that, you know, mass is the quantity of matter, and the black hole crushes all matter out of existence. So what do we end up with? We shouldn't end up with any mass. And that's where the problem is. The problem is we have a circular argument here, okay? We can't have the black hole made out of, you know, mass and crushing all matter out of existence, and mass being the quantity of matter or a measure of the quantity of matter. And there you have a couple of statements showing that, you know, what mass is officially, and that's in general, you know what it is. It's the quantity of matter or a measure of quantity of matter. You have another two testimonies there by two professors saying that the black hole crushes all matter out of existence, and that takes us to our circular argument, okay? So that's in a nutshell what's wrong with the mass notion of a black hole. You can't have a black hole be made out of mass if it crushed all matter out of existence. Period. So there's a contradiction there as well. And you know, it's up to the mathematician to clarify, you know, what the hell they're talking about. What's the other one? The other one is that they give you this vision of the black hole being a they show you a 2D scenario, two-dimensional scenario, and they are implying, sometimes they even illustrate, they extrapolate that onto a 3D scenario, and they do this sleight of hand, and of course 99% of the people miss it completely. They don't realize what the mathematician is doing. In fact, even the mathematician doesn't realize what he's doing. And what he's doing, he's superimposing a 2D scenario onto a 3D volume. And it looks something like this, okay? Here it goes. That's not the start of it, because that brings us to a second issue, which is gravity. The fact that the general relativity invokes Newtonian gravity. Here you have the 2D scenario, okay? That's flatland. They turn it around, turning it into a ball in space or space-time. Then they turn it back into the 2D scenario. Now it's a surface type of thing. You're looking at the surface of the black hole. You have stars falling inside the hole, and the question is, why don't they fall upwards? And they don't put this because, again, you're here on Earth, things fall to the floor. You let go of the spoon and it falls to the floor. And so it falls downwards. And people are used to that. But can you imagine if they were to do that, if they were to show you, the spoon falling upwards, the balls rolling upwards into the black hole that's facing upwards? Because again, this black hole, there's no reason for it to face downwards. It could be facing in any direction out there in space. So why does it face upwards? Well, because if they showed you this, then people would have a lot of questions and say, well, why did the balls fall upwards, Mr. Mathematician? And so he would have a lot of questions to answer if the balls fall upwards. And so they'd rather have you see it downwards, because everybody can understand this just by looking at it. But again, you're looking at a 2D scenario. Okay, the question you got to answer is, the balls fall downwards or upwards only due to gravity. You got to find out what the source of gravity is. And then, because that ball should not fall into the hole if gravity is upwards. Okay, so if somehow I can make like I can make a hole inside the ground in a flower pot, I'll make a hole in a flower pot, right? And I'm in space, and I'm facing the Earth, or I'm facing the moon, I'm facing a celestial object. Will the ball fall into my flower pot, or will it fall towards the, to the moon? Well, the ball falls in the direction where gravity is pulling. And if it's almost like a magnet, in the sense that, I can drop a metal ball inside a hole, but if the magnet is out here, it'll pull the ball upwards, and the ball won't fall in the hole. And this is the same thing with gravity. Gravity is what pulls the little ball into the hole. Otherwise, the ball doesn't fall into the hole. And see, they just take for granted that what you're staring at, and let me put that back up here again, they're taking for granted that you understand what's going on, that the ball just naturally falls because of the geometry of space-time. That's not true. That invokes Newtonian force. That the only reason the ball falls into the hole is gravity is pulling it down there, and that is due to Newtonian force. So general relativity does already embody or include or invoke Newtonian force. Balls otherwise don't fall into holes. They fall where gravity pulls them. Okay, and what does that do? Well, it takes us to the issue where they include the 2D scenario inside a 3D volume. And it looks more or less like this. Here you have a black hole, and everything looks normal, right? What you see, this thing just flying in space, this tornado. But as soon as you see the hole here, right there, you've just entered a 2D scenario. Now the question is, what is the hole into? And when you get into this scenario here, now you are looking at the black hole as if it were on the surface of space-time, or space or space-time. They're treating space or space-time as a box, or as a balloon, or any way you want to imagine it. And the hole right here is floating in the middle of space. You say, okay, I can understand that. But right here, now it's no longer in the middle of space. Now this scenario is 2D. And the question is, first, you're looking at it like if it were on the surface of something. And second, when you go in here, the question is, what is that hole into? Isn't that hole into space? I mean, we were in space right now. That's space, right? And now you're looking at that bottom twirling there thingy. And so that's what you're going. So you should be looking at space there. You know, why should you be going into another universe? Why are you supposed to be going through a wormhole if that hole is always within space? You know, suddenly from here they go into Oz. You know, you go to see the wizard. That's the problem that we've got with the scenario. They turn this 3D scenario, this 3D tornado, into the entrance to another universe, into a wormhole or whatever. And that's where the problem is, because that whole thing is within space. There's no reason for you to think that that is going to, make a little hole, a little entrance to another universe. Why would you conclude that? If this thing is twirling in space, right? And you're going to enter the hole, well, you're going to enter the hole, and hopefully that hole is, somewhere in space. It's all contained within space. Why would you end up from there into another universe? This is just ad hoc. They just took the magic wand and they said, yeah, it is so. There's no reason to have that conclusion. So all these things you got to keep in mind. Okay, and here again is, I put this up in a core question I answered today, just so that you can see what I'm referring to, a little, just driving it a little further. And it goes something like this. It's my Swiss cheese analogy. Let me get that smaller. Well, it goes something like that. Anyways, it's a Swiss cheese analogy, okay? And what it is, when you look at a Swiss cheese, you can see the hole because it's on the surface. And that's the same thing you see on the right over there. The black hole is on the surface of space-time when you're seeing it in that format, when they present it to you in that way. And if you were to put either the Swiss cheese hole or the black hole in a volume, like in this case, I put it in a fish tank, just to give you the idea. That's what space is supposed to be. They say that space is 3D, space-time is 4D, neither one of them is 2D, okay? So if you were to put the cheese hole or the black hole in a 3D volume, such as, in this case, a fish tank, or in space, whichever one you want, you've got a 2D scenario planted onto a 3D volume. And that is surrealistic. Okay, you can't have that. What you need to figure out is what is on in the bottom picture in the fish tank scenario. What is on this side of the black hole? What is on this side of the Swiss cheese hole? And the answer is very clear. It's what you would see on the two top pictures. You are staring at the surface of something. And they include this hole, and they include both the black hole and the cheese hole. They're including it in a 3D scenario. That's the problem. But you can see that in the case of the cheese hole, if you were to cut a little slice of it and put it inside your fish tank and stare at it, well, you would be looking at water. It's still within the water, right? And the question is, why? I mean, when you put that cheese hole inside the fish tank, are you going into a different universe? No, hopefully that 2D scenario just takes you inside the fish tank, because the whole cheese is contained within the fish tank. And that should be the same thing for the black hole. There's no reason for this black hole to take you to another universe through a wormhole or whatever. So this is where these people are cheating, or they get bamboozled by their own images. They can't visualize their own scenario. Okay, they can't imagine this star, 3D star, in a 3D volume, just getting smaller, smaller, and smaller, and turning into a 2D entrance to another universe. This is outrageous. This is unimaginable. It's surrealistic. Okay, and this takes us to the fish tank scenario here. I put the black hole in the fish tank again. And what you see is they put these black holes out there in space, okay? And you can see that it's swallowing, but what is the black hole into? What is that cone into? And you have them in different directions. That's the issue. Black holes don't always go downwards. And again, would the matter fall into a black hole if it's upside down? You know, what takes it to the singularity? The only reason it would take it there is if gravity pulls it there, but that's force. You know, the only way something is going to fall into the bottom of the cone to the singularity is if the singularity, you know, uses Newtonian force to draw it in there. Why would it fall to the center of mass in this case? What physical object is drawing it there? And again, that's the issue with mass. They want you to think that this scenario is the geometry of space-time. They say, oh, space-time is bent so the ball falls into the hole. Well, that's not true. See, the only reason it would fall into the hole if gravity pulls it there, whatever gravity is, something has to come in physical contact with the object that's going to fall to the center of the black hole. And so this notion that they have that, you know, that things automatically fall in the inclined plane, this is not true. The only reason a ball falls in an inclined plane is gravity pulls it there, in our case, here on Earth, the center of the Earth. That's where the mass of the planet is concentrated. And somehow, by some physical, unidentified physical means, mediator, whatever, you know, things fall down the inclined plane. But if you take that inclined plane out in the middle of space, where there's no gravity, or where you have no direction, you could be upside down for all we care, will the ball fall down the inclined plane? The answer is no. It won't fall. It'll fall to the nearest place where you have a center of gravity. So if you're facing the Earth, right? Let's say the astronaut holds the inclined plane like that, and Earth is underneath you. Yeah, the ball will fall in that direction because the source of gravity, the nearest source of gravity, the Earth in this case, is below you. If you have the inclined plane and the Earth is above you, the inclined plane will be in the opposite direction. The ball will fall upwards. And so what we have to identify is not say, oh, it's the geometry of space. No, that's not true. The geometry of space is only a visual sleight of hand. The only reason the ball will fall inside a hole, like, you know, when you play marbles and it falls in a hole, or you play golf and it falls inside the hole, the only reason the ball falls in the hole is gravity pulls it there, whatever gravity is. And that's what we have to identify. We have to identify what is gravity, especially here on Earth, on a micro scale, because general relativity doesn't work here on Earth. General relativity is a macro scenario, is a cosmic scenario. You can't, that's the problem they have with quantum mechanics. That's why they're irreconcilable, because here on Earth, it's quantum mechanics that takes over. You got to explain this with quantum mechanics stuff. And what is quantum mechanics? Particles. So you have to explain it with particles. Out there, you can use warp space kind of thing, but space is not big enough here to be warped, to let go of the spoon and say, oh, because space is warped, the spoon fell to the floor. That's not true. You got a couple people on the internet, YouTube, that say, oh, look, we're going to do some space warpage here in the basement or here. It's ridiculous. Einstein's theory, field equations only work out there in cosmic scenarios. Okay, so when they talk about curved space, they're talking about macro curved space, not tiny curved space here on Earth. And so when you let go of the little ball, like golf ball, the only reason it falls into a hole is gravity pulls it there, whatever gravity is. And that's what you got to identify. You got to identify what causes the force of gravity. And that takes you back to Newton, because, you know, warp space only functions thanks to Newton, because Newton's force is pulling it there. And that's what you got to identify. You can't say mass pulls it there. And then what is gravity out there? Well, it's the space-time geometry. You can't say that. It's irrational. and it violates what mathematics already has shown, for centuries, for sure. Okay, so what's the other problem? The other problem is that these people, we have our famous Nobel Prize winners, what was it, 2017? And they won the Nobel Prize for what? For discovering gravity waves. They were searching for those gravity waves at least for 30 years, I think it was. LIGO started, I can't tell you when it started, but I know they've been around for quite a while. And they had invested at least $600 million, probably more, in the project. All these engineers, technicians, and scientists working there. And they have built these detectors and so on in at least two different places. I think one was in Washington, the other one in Louisiana. And so what happened? They, you know, they were wasting money, uh, more or less like the NASA program for interstellar travel. They finally had to close it down because they couldn't figure out a way to go to the nearest star, and so they finally shut it down. Well, this was something similar. They were going to shut these people down because they were, what are we paying you for? And they had to come up with something. And sure enough, they waited until they got to Einstein's 100 years of, the celebration of 100 years of general relativity. And they said, oh, look, 100 years, just the anniversary, and we were able to detect gravity waves. So what are gravity waves? Well, the way they detected it, or this is the theory, that in mathematical physics has a way of converting itself into proof. It morphs into proof. They speculated, assumed, or inferred that two black holes collided sometime, millions of years ago. And the collision created these powerful gravity waves. And these gravity waves traveled all the way to Earth. They were listening with the LIGO detectors, and they were able to listen to gravity waves. We detected gravity waves, and they have their own reasons and explanations for why they know these are gravity waves. Okay, what's the problem? The problem is that gravity waves do not propagate in liquids, and they do not propagate in gases, and for sure they don't propagate through nothing, which is what space is. Nothing. Zero, zip, void, vacuum. They do not, but they have this idea that, light waves, they don't need a medium through which to propagate. And that's misleading, because what they changed, they did a sleight of hand right there on you. See, we're not talking about the medium through which light propagates. So to say that light does not need a medium through which to propagate, they're talking about the medium, not about what light is. So when they say that, they just switch something on you. They're not talking about what light is itself. Is light a medium? And so they change it and they say, well, light does not need a medium through which to propagate. And so it's like saying, are they talking about the fish or the ocean? See, the question is, if the fish is a wave, then we can talk about the fish. We can say, look, waves are mediated by fish, and then you can understand it, because these little fishies, they move up and down, they vibrate, and you're talking about the fish. But if you say, well, the fish don't need an ocean through which to propagate, now you change the scenario, the context. You're talking about the ocean, not about the fish. And that's the issue with that statement that is ubiquitous also in mathematical physics. They talk about light not needing a medium through which to propagate. And that's more or less the situation with gravity. Does gravity need a medium through which to propagate? And what these people are saying is, look, if these gravity waves come all the way to Earth, well, if they're transverse waves, they can't do it through liquids or gases. It must be a solid. It's got to be a rigid type of object. It's got to be steel. Okay, it's got to be a chunk of steel. Then you can propagate transverse waves through it. And so that's one choice. The other choice is to say, well, they do it through the vacuum. And gravity waves don't need a medium through which to propagate. Again, they're referring to space and not to the gravity wave. We want to know what the gravity wave is, okay? And so there's two problems. One is that, like I said a minute ago, the waves are something that's on the surface. In fact, I have a picture that's somewhere here. Where is it? Waves are what are surface phenomena. Currents are what goes underneath the ocean. You can't confuse waves with currents. If you talk about what's going on inside the ocean, you got to use the word current. There's no such thing as waves in the bottom of the ocean. Those are known as currents. And they have a different, and so, in the case of waves, you have air serving as the medium to which they propagate. In other words, they go up and down against the air. In the case of currents, it's all water all the way. So the question is, what are we talking about when we talk about gravity waves? Are we talking about currents or are we talking about waves? Waves is out of the question because it would have to be a surface phenomenon. In other words, the gravity waves can only propagate on the surface of space-time. So they're talking about currents and calling them waves. That's the first problem. The second problem is, okay, these waves, do they need a medium through which to propagate? See, if they need if the wave can only be a vibration of a medium, that medium has to be solid. It can't be a gas or a liquid. It's got to be a solid. And here we have proof, as always. I like to introduce proof because that's all that the mathematicians understand, and they want you to put proof. And here's Mr. David Blair, and he tells us in no uncertain terms in his book. And, this is a big shot. Look at all his titles. He's got an impressive resume there. He's got all kinds of titles and gold medals. He's a complete Olympian. Anyways, he's got a lot of credentials. And he says, this is what he says. This guy's a professor, okay? He says, space is a very tangible material with tangible properties like stiffness and shape. Okay? I wish he would draw it so instead of talking about it. I wish he put a picture in his book because, his book doesn't have that. It just has words. And he says, the most important thing to keep in mind about Einstein's universe is the fantastic stiffness of space, of the rubber sheet, if you like. The stiffness of solid steel is about 10 to the 11th. Space has a magnitude of about 10 to the 43rd. Space is a billion times stiffer than steel. And again, this guy is plagued with credentials. You can see him there on, he wins a prize every year almost, okay? He gets all, like the 2005 there, he is awarded by the government Center of Excellence a grant to develop the Australian International Gravitational Research Center. And so he works on gravity. He does all, especially gravity waves. He's into this thing. And this guy starts out by saying, that space is a physical object. Okay? And so the only thing he's got to do is first draw space if like he says, it's got shape. I'd like to see the shape of space. And then I would love for him to tell me how come it is that our astronauts go out there and never scratch their elbows when they're out there in space. So, these are the people who govern mathematical physics. These people are saying that space is a physical object, not only a physical object, but it's stiffer than steel. Complete nonsense, idiocy. These people are not real anymore. And I don't know what to tell you. These are the people who run the world of science, of math, of physics, quotations there. Okay, so again, if we have that scenario, they're not talking about waves, they're talking about currents, okay? And if they're talking about currents, we're talking about this wavy current, okay? These transverse waves, it's got to go through a solid. And yes, what they did is they had to convert space into a solid physical object, a very rigid physical object, in order to get their waves through. And so I guess some people will take that that version. Other people might say, well, no, see, the wave doesn't need a medium through which to propagate. And they're referring to space. They're saying, see, space is nothing. Okay, keep that in mind. They're insinuating or telling you outright that space is nothing. And so the wave has no problem in coming all the way to Earth because transverse waves don't need a medium through which to propagate. Okay, so it's the vibration of nothing. Well, they're not referring to the entity that's vibrating. They're referring to the medium through which the transverse wave is going. Okay, so again, you got to keep that argument in mind. They do a switcheroo on you. They do a sleight of hand there. And that doesn't work anyways. And let me tell you why. Because in quantum mechanics, in mathematical physics, space is made of particles. Okay? You have negative particles, positive particles. They're virtual particles. They get together, the black particle with the blue, with the white particle, or the blue with the red, and they form a no particle, I guess, because you still haven't explained what happened to the particle. I guess there's a particle still in there. It's just not a charged particle. It's no longer positively charged or negatively charged. The negative kind of neutralized or blended with a positive and vice versa. So that there's still a particle there. It's just a particle that's not charged. And so space is made of particles. So you still haven't gotten rid of the problem. You can't say the transverse wave does not need a medium through which to propagate, because in mathematical physics, space is a medium, a physical medium. It's made of particles in one instance. It's stiffer than steel in another instance. It's a solid that's vibrating. That's how the transverse wave moves through the solid, through this piece of steel, right? And so you haven't gotten rid of the object, of the medium, of the physical medium, either way. And that's because mathematical physics had to convert space into a physical object in order to get their theories across. Because they cannot understand how things can act at a distance unless space is some kind of continuous medium. That's where it leads you to that problem. So they had to convert space into a physical object, and obviously they had to convert that anyways into a physical object based on the Big Bang explosion. If Big Bang created matter, and this matter is expanding together with space, because space is also expanding. Well, if space is expanding, what is it that is expanding? Well, obviously a physical object is expanding. We're talking about a balloon. So you can't say that space is nothing, not in mathematical physics. Under any circumstance, whether you take the expanding balloon, whether you take quantum mechanics, which says that space is made of particles, virtual particles, negative and positive particles that blend and become no particle, or whether you take the stiffer than steel version, in every instance, space is a physical object in mathematical physics. So again, you can't say that the transverse wave is propagating through nothing, not in mathematical physics, because space in all circumstances and under all scenarios is a physical object in mathematical physics. Okay, and just a final problem I like to always show this, and that's the transverse waves, assuming that gravity waves are transverse waves, which is what they are saying, not me, but that's mathematical physics. They're slow. So they're the slowest thing we know. They're the slowest types of waves. Here you have the snail, that represents the transverse wave, the turtle, the longitudinal wave, and we have the cheetah representing the torsion wave, a 3D torsion wave, which is on a rope, a torsion. And the good thing about the cheetah, he travels both ways. whereas the other guys only travel one way. So that's why the cheetah is going back and forth in both directions and going across itself, because the torsion goes in both directions. Okay, and so transverse waves are slow compared to to longitudinal waves and compared to torsion waves. And you don't have to take my word for it. I mean, just go ahead and just take a rope, tie it tightly, because I've done this, and I've got it filmed. And you just take a rope, tie it from one wall or from one post to another post, two poles. Okay, just tie it, make it as tight as you possibly can, and then just put two clothespins so that you have something to look at. And just move one clothespin. The other one moves instantaneously. And you'll see how fast torsion wave is. It just goes whoom. You can't even film how fast it is because it's instantaneous. Here on Earth, I mean, if you just take a couple meters, it's instantaneous. And of course, there is a delay from one clothespin to another. If you stretch the rope from here on to the moon, which is a little over a light second away from us, and if you had a rope connected from one end to the other, well, if you move one clothespin, the other one doesn't move instantaneously. It'll move at 300,000 kilometers per second. That's how fast the torsion wave, right, would propagate through through the rope, through this tight rope, if you could stretch it tight from here to the moon. The other thing about a torsion wave, just throwing it in there, is yes, it's not a 2D scenario like the transverse wave, and it's not we'll call it a 1D scenario. You can imagine that longitudinal wave. Torsion wave is a 3D wave because it's a rope. It's the thing that's twirling. And of course, you can put a 3D rope in the middle of space and torque it, and you won't have a problem. You're not cheating on conceptualization. Some people say, well, Bill, a rope is just a concept. It's just you're just replacing that with another concept. No. A rope is a physical object, you dummy. Go to the hardware store, ask them for a longitudinal wave, ask them for a transverse wave, see what they give you. Ask them for a rope and see what they give you. And torsion is what the rope does. So yeah, rope is a physical object. It's not a concept. What they're confusing is the fact that I'm simulating light. You could use it for gravity there, but that's not true in the case of the rope model. But we're simulating light with a rope. We're saying there's a physical object there that we can't see because it's so small, so thin, that torsions go through this object, okay? Let me move along and show you something else I want to show you today, and that goes in relation to also what we discussed the other day, what's causing black holes phenomena, what's causing all this. And I start by showing you a galaxy. That's more or less what a galaxy would look like if you see it from Earth. And of course, what you can't see there is the magnetic field of the galaxy. They never put that in there. They just show you the galaxy just rotating, okay? And so that's a little misleading because there's something we can't see in there that we know is there, which is the galactic magnetic field. And we really have to get more used to seeing the magnetic field. So what do? Well, under the rope model, we have to put there you have the spider's web, and because all the stars are interconnected, and we put this on top of the galaxy just to illustrate that all stars are interconnected. Okay, so when the galaxy rotates, you got to think of it as all stars being interconnected. So now we can explain dark matter, for example, very easily. We can say, look, the reason stars on the edge of a galaxy don't go flying out is that they're all connected. That's the first one. And the second one is the reason they go so fast, faster than the ones on the inside to keep pace with the one that's on the inside, is that a galaxy is like a platform. The whole thing rotates simultaneously like, a bicycle wheel or a carousel. Okay, so that's how you have to think about it. Now, on top of this, what we do is we superimpose the magnetic field of the galaxy, okay? So you have to think of all the stars are interconnected. Now we're going to put the magnetic field. And one of the issues that came up with Peter the other day is whether the magnetic field, how far does it extend? And he had the idea, the notion that maybe the magnetic field does not extend very far, but he's referring to the strength of the magnetic field. He says, I don't think the magnetic field extends out there very far away. And again, this is just opinion. We have no way of knowing how far a magnetic field of a galaxy stretches. All I can do is give you a similar scenario, and that's the magnetic field of the sun. We know the sun, the magnetic field, extends way beyond the, Pluto. Magnetic field of the sun is what keeps it protected from interstellar matter, from the from all the things that fly intergalactically and interstellarly. That's we have this cocoon, this protection, and that's caused by the magnetic field, the heliosphere, and the all these notions, all these things that they've already measured primarily through some of the probes that they sent out there. The magnetic field extends very, very far away. If the magnetic field of the sun extends so far away, then in the same way we can think of the magnetic field of the galaxy. Let's see if I can put it back up here. Should extend way beyond the last star. And if this is the case, right? Not that it is, but I'm just speculating here because I want to give you a notion, something that came up in my mind, my crazy mind, and see if you want to consider it. I'm saying that here, what's causing the movement of black hole, there, the little white dot that's moving, is the magnetic field of the galaxy. And there's nothing wrong with considering that as a possibility because a charged ball here on Earth moves in a magnetic field. Also, it spirals in a magnetic field. And that's what I have there in the little scenario on the lower right. So magnetic field has the potential of moving a magnetized object, such as a star that has a magnetic field. It has the power to move it around. The only question is, well, there's a couple questions. Whether the black holes are near the center of the galaxy, in which case we have no problem with the force of the magnetic field because it should be quite strong near the center of the galaxy. The question is whether we can see any black holes on the periphery of a galaxy, okay? And also, we know that the magnetic field has the ability to suck in gases, like it's showing there. Why? Because here on Earth we have, there you have a rotating magnetic field, and you can see it swallowing smoke. It draws the smoke inwards. So the smoke, we can't feel the magnetic field. You pass your hand there, you don't feel anything, but the smoke is absorbed, it's sucked in. And so we can just as well assume that all those gases that are being swallowed by nothing, by what they say is a black hole, well, this could be swallowed by a magnetic field. We do not need to have a black hole mass. We do not need to introduce mass into this scenario. We can do it with magnetic fields. But this is what I wanted to show you. I wanted to show you that, what happens if two galaxies are close together. And remember, we do not see the magnetic field, the little lines that are going around. We just see the two little dots there. That's essentially what we would see in space. Say, oh, okay, here's a galaxy, here's another one. But see, their magnetic fields extend very far away. And what I'm saying is that one possibility is that where the magnetic fields meet, okay, where they superimpose, that could be a place also where you have black hole phenomena, black hole things, phenomena which are attributed to black holes. So you could have that situation where the magnetic field of one galaxy, which extends very far away, interferes or superimposes on the magnetic field of another galaxy, and that's probably where we would observe black hole phenomena. We would see a star twirling around nothing, we would see gases being sucked into nothing, and it's just because the two magnetic fields are interfering with each other. Just one possibilities for your consideration, okay? These are things that maybe you should consider as well as any other. I mean, if you're going to if you're going to consider black holes, you might as well consider these as well. Okay, final thing I wanted to, what is a black hole in the end? It's a point. We get back to Euclid. A zero-dimensional point, right? Because they can't get away from that notion of, this thing coming down to what? To a point. What's a singularity? It's a point, a zero-dimensional nothing. And all we can do is, put a, an ordered pair from some arbitrary reference point and say, oh, there's a black hole over there, see? But you can't see it, it's zero-dimensional. Yeah, because we need two numbers to locate it here in space. And they get these Cartesian coordinates and they say, see, here it is. It's 5 paces to the left and 2 to the north. Okay, so that's what it is. Well, so okay, and what was the problem with the point? We had moved into onto the point before I went off into JFG's program, and so I want to get back to that because I really want to cover a little bit of geometry in a couple of the sessions. And what do we have? The problem with the point is that we don't have a definition today, and it starts with geometry. What is geometry about? Because that's where the point belongs, right? It belongs in geometry, and it says geometry is a branch of mathematics that deals with shapes and sizes, And so I'm not sure how a point is going to fit into shapes and sizes. That's where we're going to have the problem. And so geometry may be thought of as the science of space. Okay, great. So they're talking about space, referring to, the three-dimensional space, because they think space has dimensions. Or that's the way it's come up with. When they talk about space, they're really talking about objects, and they're saying, objects have dimensions. But they call that space, okay? And so contorted the language that they use. And so geometry, this is from one side, and it just kind of summarizes the problems with geometry, with Euclid's geometry, right? So geometry combines simple conceptual building blocks to construct complex logical structure. These building blocks include undefined terms, defined terms, and postulates. So they start out on the wrong foot. They say, look, we're not going to define our terms, but just follow along, follow our theories, our proofs, or whatever they got in geometry. And they continue, some concepts central to geometry are not defined in terms of simpler concepts. No kidding. The most familiar of these undefined terms are point, line, and plane. So we have already a problem there. We're not going to define the point, but we're going to build all, that's going to be the building block. We're going to build everything with points. We're going to build the lines, the planes, and the solids with points. And they start out by saying, Jesus, we don't even have a definition for point. And so what is the notion they have a point? Well, they have two notions. That's the problem. It says the experience of where an object is leads to the idea of an exact fixed location. So we have where and we have location. That's the notion. And this is the intuitive idea to which the term point refers. They're referring to where and to location. And then they immediately do this sleight of hand. They say many physical objects suggest the idea of a point. Well, what are we talking? What do you mean? An object is a point, and they're talking about where and location? Hopefully an object is not a location. And so they go on and say, well, examples include the corner of a block, the tip of a pencil, or a dot on a sheet of paper. All those are objects. They're not locations. They're not wheres. They're not places. And they say such things are called models or representations or pictures of points. Okay, so they're representing the point with this pictorial thing, and at this point they lost you because you don't know if they're talking about the where, the place, the location, or they're talking about the dot, the tip of the pencil, or the corner of a block. Which one are they talking about? And they say, although they show only approximately the idea in mind. Yeah, the approximate idea is that, we still don't know if the point refers to location or to the object, to the dot. That's the problem. We don't know whether the point deals with one or the other. Similarly, a row of points suggested by a tightly stretched string, the edge of a desk, or a flagpole extended infinitely in both directions is called a line. So, they have all these definitions or all these notions, and this is just in every book you'll find this of geometry. This is how geometry is explained to you, when you're in high school and college. They explain it in that same way. Okay, so what's the problem? Well, here you have, these are official books, by the way, okay? Here you have two books. The bottom one is a book. The top one is a reference on the internet, but they come from reliable sources. One comes from the Math League. The other one comes from Dr. Math, who has this book on Amazon, so you can find it there. And so they define what a point is, and they say, we may think of a point as a dot on a piece of paper. Okay, so now you know what a point is. It's a dot. We're done. Okay? That's what they drew, right? You see these letters A, C, Q, and B. They're dots, little red dots, right? I mean, do you have any questions? It's straightforward. And he says, the Math League says, we identify this point with a number or letter. Great. Okay, fine. We give it a name, Johnny, Peter, Louis, no problem. A point has no length, width. It just specifies an exact location. Well, those points have width and height. You can see it on the bottom right there. It's got height and width. That's what a point has. That's what a dot has. And they say it's not supposed to. That's just, they're using the dot to represent the point. And what is the point? Well, it just specifies an exact location. So we got a circular argument. We still don't know whether the point refers to the dot or to the location. And you say, well, Bill, obviously they're referring to the location. The dot is something that they use just to represent the location. You can't do that. You can't do that for at least two reasons. One is geometry. What was the definition of geometry? It deals with what? With space and size. If the point, the word point refers to location, we're not talking about shape or size. You can't say that the point belongs to geometry because if geometry is about shape and size, you can't say that location is a geometrical figure. That's the problem there. And then the other one is that they're going to use the point, the famous point, to build lines, planes, and solids. So they're talking about a little ball. A little ball that has no size, shape, nothing. It's just a little zero-dimensional ball. That's what it is. So again, we got a problem. We got a problem because if geometry is about shapes and sizes primarily, then the famous point, if it's a location, it doesn't belong as a geometric figure. The word is figure. And that will go also for the line. I'm getting close to closing here, so let me just move on. My point is that point is not part of geometry if the word point means location. That's what I'm saying. You can't have it both ways. You can't say, look, a dot simply pictorially represents location. The point really is location, but we use the dot because we have no other way of presenting location to you. No, because the dot is 2 or 3 dimensional, depending on which you want. And location is non-dimensional. It's not 0 dimensional, it's non-dimensional. You cannot talk about the dimensions of a concept. You can't talk about the dimensions of love. What does love have? Length, width, and height? I mean, you can't talk about concepts having dimensions. So it's non-dimensional. And if it's non-dimensional, no size, because you can't talk about the size of a concept, it doesn't have shape, you can't talk about the shape of a concept, then it doesn't belong in geometry, especially as a building block. And that's where we have the problem. The problem is that the word point is that another of those dualities of mathematics, you know, wave particle duality, infinitesimal means zero also, and here you have the same thing with a point. It means location and it means dot. That's what it means. So they put the dot and you say, okay, I understand. You put it, you mark the dot with your chalk on the board, okay. I follow you, and then they say, okay, now forget about all that, and now we're going to use it a location for everything else. We're going to talk about the locations on a solid, on a sphere, or on a cube. The location. What's in that location? A dot. What do you mean a dot? A three-dimensional dot? Because, I mean, you're talking about a cube, right? Is it a two-dimensional dot? No, it's a zero-dimensional dot. It's just the location inside the sphere. And that's why geometry is has a ridiculous starting point. Because if they want to talk about location, don't use the word point. Just use the word location. That's fine. That way you don't confuse us. We don't mix the dot with a location. Don't tell me that a line is made out of dots, right? Because that's what you're seeing. And that what you're staring at is a one-dimensional line. No, what I'm staring at is a two-dimensional elongated box. You know, two-dimensional at least. That's what's in front of me, objectively. And how can you build that? How can you build a one-dimensional line with zero-dimensional points? Well, because they're not talking about dots. They're talking about locations on a line. But then you can't talk about points like if they were discrete little balls comprising the line. And I'll continue with line on the next lecture. And that's going to be this Wednesday, so stay tuned. We'll see you then. Bye-bye.